Hi, this is David Greenberg. Welcome to episode 22 of the Machine Learning at Helmholtz-Zentrum Gestalt seminar. We have a really exciting, interesting paper, and we are lucky to have the first author with us today. We'll get to that in a few moments. First, we have a brief announcement from Tobias Weigel from DKRZ.
Yes, so just an announcement. So I would like to invite once again everyone who is interested in ML for a system analytics, modeling, also impact research to attend a workshop we are planning. It will take place May 3rd and 4th in the afternoon. It's free of charge. It will be a fully online virtual event. Registration is open. We already have about 130 participants registered, but still more to come. And particularly if you're interested in presenting your own work at the workshop, please feel free also to apply for that. I'll share a link here and also in the YouTube stream, possibly if that's okay, where you can still apply. So yeah, we've got a couple of open spots still. Other than that, of course, you're always free to register and just listen in. So thanks for David for giving me the opportunity to share this here again. And then I think we'll get started with the content here.
Great, thank you, Tobias. And I will now turn over to Shivani Sharma, a PhD student in our research group, to introduce today's topic.
Hi, everyone. For today's seminar, we have a very special guest with us, Axel Seifert from the German Weather Service, who will be presenting his work that's been published in the paper Potential and Limitations of Machine Learning for Modeling Warm Rain Cloud Microphysical Processes. In some of our past seminars, we have talked about papers where machine learning models have been used to replace for replacing physics-based parameterizations in atmospheric models. In particular, in episode 17 and 14, we talked about radiation and convective parameterizations. For today's paper, today's paper explores how machine learning can possibly be used for microphysical parameterizations. So Axel is going to give us a broad idea about what are the different processes that need to be taken care of while designing a microphysical parameterization, and also introduce us to the main parameterization that's been used here, which is the Superdroplet method. There are some very interesting results about how the neural networks basically are able to learn the process rates that have been calculated using the Superdroplet scheme. The neural networks are then used to estimate the long-term evolution of the process rates, where surprisingly, results are not as we would expect. And now I hand it over to Axel for getting started with today's presentation.
Okay, thanks a lot, and hi to everybody. Yeah, thanks for inviting me to this seminar. It's for me also quite exciting to be able to connect to machine learning experts because I'm what you would call a domain scientist. So I have no background in machine learning. And for me this paper or this little project was just kind of a first step to learn a little bit more about this in an area where I feel most comfortable, which is this warm rain cloud microphysics. It's actually a topic that I did 20 years ago as part of my PhD thesis that I now picked up again using these machine learning techniques. So, for today, I think I will give a bit an overview about the basics of clouds and cloud microphysics and their parameterizations. Then I will introduce the so-called Superdroplet algorithm, which is a really nice technique to build a benchmark or a reference model. And then, of course, the main topic for today will be the question how we can use machine learning methods to learn or derive or develop such bulk microphysics parameterizations based on these superdroplet simulations. And for that, I simply use Keras or TensorFlow, that you probably all know. And then I give you some conclusions and outlook at the end. So what's cloud physics? It's, of course, the area of atmospheric science that describes the formation of clouds and precipitation in the atmosphere. It's a big area of research, of course. It's important to know that clouds in the atmosphere or cloud particles form mostly from heterogeneous processes, nucleation, and that requires aerosol particles. So it connects to all the kind of dust and particles in the atmosphere. Then cloud physics is mostly about thermodynamics. So these particles grow by condensation or deposition of water vapor. But then the interesting thing is really that these particles can then collide with each other, and they grow by these collisions. So the particles we also call hydrometeors, so because they are water, and every particle in the atmosphere is actually called a meteor in meteorology. And the collision rate is dominated by the difference in the fall speed, so what we call differential sedimentation or gravitational collisions. Then clouds are, of course, very important in atmospheric models, as most of you probably know. And that's because they release a lot of latent heat during condensation, and that drives atmospheric dynamics and circulations. They, of course, also interact with radiation, and that changes then the energy budget and also affects then circulations. The precipitation is, of course, very important for the water cycle, obviously. And as I said, because of this connection to atmospheric aerosol, the aerosols can affect cloud properties and hence climate, which is a very important research topic in climate modeling. And for all of that, we need parameterizations, which are just kind of schemes or techniques that we use to describe clouds in the atmospheric models. But to start, we really formulate the more fundamental cloud physics theory in terms of so-called particle size distributions. And the size distribution here may be just f of x. It's just the number of droplets or any type of particles in a certain mass interval per cubic meter. So this is an efficient way to describe how many particles of a certain size are present in an atmospheric volume or parcel. So if we would predict this distribution directly, for example, by discretization of this function, that would be very costly because you would need several kind of grid points in the spectral space or bins. And that would become very, very expensive in numerical weather prediction or climate models. So that can be done also in 3D models, but not, for example, in real-time operational applications, and not in a big climate model that has to simulate hundreds of years. So what we do instead is that we calculate kind of statistical moments of this distribution. And because, for example, for liquid drops, we usually have small droplets that remain lofted in the atmosphere and are called cloud droplets, and bigger ones that are falling out and are called raindrops. We separate the distribution into two parts or categories, and this size or mass that distinguishes cloud from rain is corresponding to 8 microns diameter. So we have these so-called partial moments of the size distribution that we use to describe the clouds and the precipitation also in the models. And then you can, of course, pick any number of moments to build a certain scheme. Therefore, you sometimes talk about one-moment schemes when you carry, for example, only mass, or two-moment schemes when you have mass and number, for example. Or you can have 3 moments, and then people usually also use what's called radar reflectivity, which is approximately just the second mass moment if you want to have a 3-moment scheme. When we look at possible or actual cloud processes and we adopt this notion of these categories, so cloud droplets and rain, and they of course interact also with the atmospheric water vapor. Then you have processes like activation or nucleation, which creates the cloud droplets from the aerosol, and then they grow by condensation, or they evaporate when they are subsaturated. And then they can collide with each other, and then we have just special names for these collision processes. So when 2 cloud droplets collide and build a raindrop, then we call this autoconversion, and when a raindrop collects a cloud droplet, we call this accretion. And we will come later to that in more detail, but then of course also the raindrops can evaporate, and cloud droplets can just collect each other and get bigger. That's then called self-collection and so on. So there are a lot of processes, obviously. That gets even more complicated when we allow for ice phase and have kind of corresponding categories of cloud, ice, and snow, and there we have similar processes, but of course we also have melting and freezing based on temperature. So that's quite simple, actually. So this kind of scheme is what you would use in a global numerical weather prediction model or in a climate model. You have to have some ice phase, but you want to keep it simple. So you can pretty much see this kind of nice symmetry between the liquid part and the ice part, at least on paper. When it comes to the actual processes, there are quite some differences between, for example, the aggregation between ice particles or the collisions between droplets. When we go to convective clouds, things get a lot more messy, because then we get a lot of interaction in the mixed phase, and then you get all this graupel and hail that forms by riming. Riming is when ice particles collect supercooled liquid water, and you get these drops freezing onto the ice particles, and that's how graupel and hail form. Hail is just with a higher density and often involves kind of partial melting and refreezing in the so-called wet growth regime. So this is where it gets very complicated. And you can see in the end, we have a lot of processes, and the whole thing is very complicated. So you need to parameterize or quantify all of these individual processes. And you can imagine that this can be very tedious, and it has taken the community several decades to come up with schemes that work well in all this complexity. Okay, but for today, we're going to keep it very simple, and we look only at the collision processes among and between cloud and raindrops. So in fact, we want to look at what's called the kinetic collection equation, which describes this collision rate when we go back to this description based on the drop size distribution. Then you can formulate the collisions based on these terms with some gain term and some loss term. Yeah. And the physics of the collision is actually hidden in this K, in the so-called collision kernel. And here, this is just gravitational kernel, where you have some difference between fall speeds or terminal fall velocities, and just the cross-sectional area, joint cross-sectional area, which builds the so-called swept volume, which would be the so-called geometric collision kernel. And then, of course, we have the air between the droplets. So it's actually a hydrodynamic problem that we have to look at. And for example, very small droplets can follow the flow around a bigger drop. And this is then described by the so-called collision efficiency, which is, by the way, usually just tabulated. So there's no, okay, so let's go back to this autoconversion and accretion. If we are on this bulk or moment level, we want to quantify these this mass transfer, especially between cloud and rain. And this can happen by, as I said.
Dann musst du mir mal bitte deine Kopfhörer.
As I said, there can be two cloud droplets colliding, making a raindrop. That's what we call autoconversion, or the raindrop can collect the cloud droplets, and that's what we call accretion. And again, we could formulate this based on the size distribution function, and we get these integral relations. But they are actually very nasty to evaluate, especially the autoconversion integral, because of these integral bounds. So if you want to do this analytically, you're facing a very hard problem because you always have to kind of combine the corresponding masses or droplets to pass over this threshold. And this is done by these integral bounds, and that makes the integration very difficult. And even numerically, that can become really tough, because this integral bound for the autoconversion will always fall within one of your kind of size bins or finite volumes, or whatever you want to call it. Okay, so later we want to compare with the established bulk parameterization. As I mentioned, that's something I did during my PhD 20 years ago. And here we make use of two ideas. First of all, that this kinetic collection equation is invariant under transformations that involve especially the time coordinates. So if you multiply the size distribution by a certain factor, C, and you put the C in here, you can see you can immediately pull out the C squared in front of the integrals if the C is a constant, and one of the C's you put to the F into the differential, and then you have one C left over. And to get rid of this, you transform your time coordinate, and then you have an invariance transform of the equation. It's actually quite simple, but it's a very fundamental property of this equation, and it gives you self-similar solutions. So you can identify the C with your conserved property of the equation. That's actually the total mass. So the C is the ratio of the masses between these two self-similar solutions. And in the end, you can conclude from that two things. First, that your autoconversion is quadratic and liquid water content because of this kind of C squared dependency. And the second, besides that L squared dependency, you only want to have non-dimensional dimension on non-dimensional dependency on liquid water content in this kind of sense that if you have the cloud water over the total water, you have a non-dimensional variable that's also kind of invariant under this transformation, and that you can use for describing further details of the process, whatever. The other idea that you want to use is this approximate collection kernel, which has a polynomial form, but is piecewise, defined one part for the cloud droplets and one part for the raindrops. That also tells you that this to distinguish between cloud droplets and raindrops is not really something very artificial, but it really goes back to physical properties that also can be found in the collection kernel. And from those polynomial kernels, you can derive certain approximations, and you end up with this ansatz for the autoconversion rate, where you have a certain dependency, as I said, quadratic on liquid water, that comes from the similarity and from the long kernel, quadratic in mean mass that you get from the long kernel. This new here is the shape parameter of a gamma distribution in the cloud droplet space. And this dependency also comes from the long kernel. And then kind of there's this additional, what I call universal function that depends only on this non-dimensional timescale tau. So that's how a human, a scientist, approaches this problem when you have a little bit of a theoretical background. And that's kind of the idea that you can come up with. And it will be interesting what the machine learning will do. But let's first go to the superdroplet thing. When we go back to the kinetic equation, instead of using some discretization, it's actually very natural in some sense to think of a Monte Carlo algorithm to solve this collision process, because that's very close to the physics of it. So people have done that already in the 70s, but only recently some more efficient algorithms have been suggested, and especially the one of Shima et al. Is a very neat technique. These super droplets differ from droplets in that they have a multiplicity. So each super droplet represents many, many real droplets, can be thousands or 10,000s. And that simplifies or makes this whole thing more efficient. But you have to keep track of these multiplicities here called xi. And here in this example, this is very low multiplicity. So here the super droplet, the big one, would have a multiplicity of 2, the small one of 3. So when these two super droplets collide, you can only build 2 collision pairs, and one small one is left over. And then for these possible pairs, you calculate the collision rate and the collision result. Here they both collide and make a bigger drop, and you have one remaining small drop. And the good thing is that during this collision interaction of these pairs, you can do very complicated things, or physically very complicated things in a very simple algorithmic way. So that's really a great advantage of this. Another advantage that here it's very easy actually to calculate autoconversion and accretion, because you know the size and properties of the droplets before and after the collision. So you know whether a cloud droplet became a raindrop or not, and you can simply count your super droplets in a proper way, and you get these process rate. And that's also very neat about this super droplet method. So why is this also very attractive? So for the warm rain process, it's actually not a very efficient description. Here, the classic bin schemes would be more efficient or computationally cheaper. But for example, when you want to do cloud chemistry and you want to track chemical composition of droplets, then these Lagrangian particles or superdroplets are really nice. Or when you want to do more difficult, like non-spherical ice particles, as I mentioned before, they can have various shapes like columns or needles or plates, or they can do these rhyming processes, and then you have a rhyme mass with a certain density, and you want to keep track of this, for example, for rhymed snowflakes and so on. And that's something you can really do with these Lagrangian particle schemes. So for more advanced cloud microphysical questions, this is really attractive, but of course it gets very expensive and complicated. Okay, yeah. This is just to show you that with the superdroplet scheme, we can also reconstruct this phi function that shows up in this auto conversion rate, and that it really reproduces the result basically from 20 years ago. So that was nice to see as well. So now let's finally come to the machine learning. Maybe I have to speed up a bit, but as you mentioned, you know the paper basically, so I can then speed up a bit. So as I explained, microphysical parameterizations are always crucial for modeling, but they're also difficult to construct and also have their limitations. And they're becoming more and more complex because people want to describe more and more complex phenomena. And we have these really nice tools with the superparticle or superdroplet approach. We have really good observational data coming up. So the question is whether machine learning can help us to work with this complicated system and speed up this process to get from the complicated underlying theory or simulations to these bulk parameterizations. And that's what I wanted to investigate, whether machine learning algorithms could do that for us. So what we want to do is really just to see whether the machine learning can kind of reproduce this parameterization for the warm rain processes. And to do that, we do these reference simulations for the kinetic equation using this superdroplet method. We calculate the bulk processes, as I mentioned. Then we give these process rates to a neural network and train a regression model. We can, for example, use different predictors. But then we are not done, but we want to solve the ODE system that corresponds then to the kinetic equation and compare with the parameterizations that we already have. So that's the kind of usual workflow, I think, in simple machine learning problems. We want to use this TensorFlow library, but first we have to separate our data in training, validation, and testing data, because the autoconversion rates, for example, they span many orders and magnitudes, and the predictors, the features as well. So we do a log transform and a standardization, but I think this is also quite standard in machine learning. And as possible predictors, we just follow kind of the classic parameterizations. We use, for example, liquid water content, number or mass to describe the size of the droplets. We have the shape parameter of the initial gamma distribution, because we can use the rainwater content, or alternatively, this dimensionless form. And this is just of the overview of the training and testing data that I compiled based on the superdroplet simulations. So you really scan through this phase space or parameter space with the initial conditions to cover a large range of liquid water content, drop sizes, shape parameters, and so on. And we have autoconversion, accretion, and these two self-collection rates. The takeaway from here is that we have order of 100,000 data points at least for each process rate. Then we build a simple, fully connected neural net. Here just copied from my Python script, just a 3-layer with 16 nodes, so really rather small actually. And this then has like roughly 600 trainable parameters. So overfitting is not a big problem. And here's already this result for the autoconversion rate. And you can see mean absolute error, mean squared error, and different machine learning models using different predictors. And as soon as we include the rainwater content into the predictors, the models get actually pretty good and are actually better than the process rates from the classic man-made bulk parameterization. So this looks really good. So we have this kind of automatic machinery that can build us this parameterization, and I found it also quite nice that it shows that including this rainwater content into the predictors actually improves the model, which is kind of counterintuitive to people even in cloud physics, because as I said, autoconversion is just a collision between cloud droplets. Why should it actually depend on the rainwater content? That's at first sight not physical. But if you think about it a little bit longer, then it's about the size distribution. So the autoconversion is dominated by the large cloud droplets, and the presence of rainwater is kind of a proxy for the presence of large cloud droplets, and that's therefore it's a reasonable predictor, and machine learning model recovers that kind of idea. Then we did this so-called partial dependency plots to really look a little bit deeper into this neural net and its predictions. And here the blue lines are the dependencies from the neural net, and the red lines, red dashed, is from the bulk parameterization for the different process rates, just autoconversion in the first row. And you see that for all process rates and all predictors, the agreement is actually quite good. So I find it quite amazing how the machine learning algorithm can recover these dependencies. And for those variables that we neglected in the parameterization, the machine learning model also finds that these dependencies are not strong. They are rather weak. So that looks really nice and consistent. But of course, we are not done yet, or as a pure machine learning problem, we would be done. We would be happy with our predictions of the process rates, but as atmospheric modelers, we want to put this into a differential equation system and solve for these solutions. So we just put these autoconversion and accretion and self-collection rates in this ODE system and then compare on this level. And here you see a few time series. These are 4 different initial conditions in one plot. So the gray and red ones are the superdroplets and the bulk parameterizations, and the bluish lines are the corresponding machine learning solutions. And here you can see they are not as good as the classic parameterization. So here for the fast solutions, they are a little bit lagging behind, and here for this very slow evolution of the system, it's the machine learning solution. It's a bit too fast. So it's doing okay, but not quite right. And you can do that in a bit more systematic way. Here we are mostly interested in the time it needs for this solution to really get started. So we use the time that it's needed to get 10% of the water into rain as a metric or measure for how good the simulation is. And here again, we can compare this time scale of the machine learning model in blue with our two other solutions. And here the simple model that does not have rain within the predictors, that's not really good. But the one that was really good in the process rates has a reasonable shape. So the dependencies are actually not bad, but there's a offset. Overall, there's a delay here, but it's not too bad actually. Here, that's the dependency on radius and shape and liquid water content. Again, the simple model, not good. The more complete model that has this tau as predictor is again doing okay, but not as good as we had hoped. So why is that? Let's look a little bit deeper into these time series of individual solutions. Here, this is one case that's already quite difficult, so it takes more than half an hour to produce rain. And when you look at the process rates, you can see the black line is the order conversion from the Superdroplet Monte Carlo. As you can see, it's a bit noisy, and the accretion rate is here in this dashed line, where you cannot really distinguish the black and the red because they almost fall onto each other. But only for accretion, for the order conversion, the bulk parameterization overestimates, quite a lot in the beginning, while the machine learning model tries to reproduce the actual time evolution of the reference solution because it was really trained with that. And this is actually a bad idea here because these order conversion rates from the superdroplet scheme are very, very low in the beginning. So there's almost nothing happening in the beginning. And that leads to the fact that in the end you get this delay. But why is this behaving so strangely here? Becomes even worse when you go to even slower solutions where it takes more than 2 hours to form rain. Then for the first hour, you see pretty much nothing in the benchmark solution, which is also our training data. But the classic parameterization has some order conversion rate already early on. And the machine learning model tries to be closer to the training data. But as I said, that's maybe not a good idea here. And why is this not a good idea? That's because we have a so-called closure problem, or at least in kind of physics or in atmospheric science, we call this a closure problem. When our simplified model that we want to build cannot really describe the full complexity of the underlying system, and we need some, closure, you could say, some trick to make it work. And here the problem is that in the very first stage, the cloud droplets, they collide only among each other and form no raindrops at all. So this will not affect the variables in our two-moment model because it does not change the number significantly and not at all the mass of the cloud droplets. The physical system actually changes the skewness of this distribution. But unfortunately, we decided to not have the skewness as a model variable. And you could say that that's our mistake when we design or pose the problem. And that's what makes it so difficult for the machine learning algorithm to come up with a proper solution, because there's some part of the parameter space where our model cannot really work properly. So our problem is kind of ill-posed, at least in some part of the parameter space. So how does the bulk parameterization overcome this problem? As you have seen, it makes the autoconversion much larger in the beginning. It always has a positive, definite, and really significant autoconversion rate. And then it actually compensates this by decreasing the accretion rate early on. And to balance this out, it makes use of this similarity of the solutions. Otherwise, it would be really difficult to construct and build this. But this is something, of course, that the machine learning model, at least in the way I trained it in this exercise, would never be able to do. It just follows the training data. So I think this does show that machine learning can be used to parameterize cloud microphysical processes, for example, using these Superdroplets. So I think it really can do this. And even the simple approach, training the process rates with standard methods, works okay. This conversion problem itself is challenging, as I said, because it's kind of ill-posed, and the way we train the machine learning model and the way the training data looks like makes it kind of impossible in some parts to solve this. So to overcome this, one could go to a 3-moment scheme that kind of includes kind of the skewness of the distribution as a prognostic variable. That could probably be done very efficiently with this workflow and this machine learning techniques. But the price to pay that also your model later on will be more expensive and more complicated. So not sure that I want to go there. And the other alternative that might be a way forward is if we go to more advanced machine learning methods that train not only on the process rates, but would take into account these full ODE solutions to also kind of balance this approximation between getting the process rates right and getting the overall solutions right. Okay, so this was my overview and my talk for today. Thanks for your attention.
Okay. Thank you very much, Axel. That was really interesting and informative. Let's see if we have questions from the Zoom chat or from the YouTube chat. I know I have a few questions, a few things I'd like to know more about, but do we have anyone else who would like to ask something or any comments? Let me ask one question while we're waiting for more from the chat, and that is, so for both the machine learning methods and the bulk parameterization scheme, you actually provide the shape parameter of the, as I understand it, the initial distribution of droplet sizes, right? So it's a gamma distribution and you have a shape parameter, and you provide this to either the formula for the process rates in the bulk scheme or as an input to the neural network, right? So my
Yes.
question is how, if you were to use this bulk moment scheme in an actual numerical weather prediction or climate model, where would that shape parameter come from?
Okay, that has something to do with kind of the underlying aerosol distribution or particles. So when you have many aerosol particles or more kind of continental polluted regime, then your cloud droplet distribution will end up having more particles, but it also will end up being more narrow. While in a more maritime regime, you will have fewer cloud droplets, but at the same time, a broader distribution. So this shape parameter is only there to describe these different kind of aerosol regimes, but in these two moment schemes, it's really kind of a constant or it only describes kind of the underlying aerosol distribution or the initial cloud droplet distribution kind of after this nucleation condensation step. But it does, of course, not describe the change of the distribution during this collision coalescence stage. And that would be necessary to overcome this autoconversion issue, or that you would have to do in a three-moment scheme. But this also tells you a little bit how difficult it would be to really go to a three-moment scheme, because this whole complexity you would also have in your interaction with the underlying aerosol. So and even, for example, mixing with environmental air changes your shape parameter and so on. So this doing this correctly, this shape parameter is very challenging, actually.
Well, that's really interesting insight. There's another question from the Zoom chat. Hagaman from HZG asks about any observation data that could be used to evaluate the simulations.
Yeah, there are some people who have tried to measure what they actually say they measure autoconversion, but what they actually measure are cloud droplet or drop size distributions a few minutes kind of apart. And from the difference between these measured distributions, they then try to estimate autoconversion and accretion. That can be done, but it has a lot of issues because you have to take an airplane, fly through clouds. You have a certain measurement volume or length, and you cannot just stay in the cloud and follow a cloud parcel or a certain distribution. And if you would do that, you would actually disturb the cloud, and you would also not have a proper observation. So it's really challenging to get good observations for this. Therefore, I think it's really more a theoretical problem that you approach with, good simulations and understanding, and you can do these benchmark simulations. So what would be really nice would be able to do a really good DNS superparticle simulations, and now people are working on that. So.
That's quite interesting too. I have one more question, though. I think we have time for one or two more from the Zoom chat. I don't know, Toby, you're looking at the YouTube chat. Just let us know if there's something. So, I mean, looking at figure 7 of your paper, which I think you showed us well today in the presentation, the bulk moment parameterization does a pretty good job. Maybe not so great at very low density of water, but overall it really matches the Superdroplet scheme quite well. It seems in figure 8 to do a little bit less well at getting the timing's right when you have, again, these more peak distributions with higher shape parameters in your gamma. I'm wondering, in general, can you say anything more about the limitations of this bulk moment scheme? And are there any places where we might hope to do better with the machine learning method? Maybe when we couple it to the atmospheric dynamics, then these subtle differences become more important?
Yes, so the bulk scheme works almost perfectly in this box model framework, because that's how it's designed. And yeah, this, for example, the similarity solution approach or this invariance thing is of course only a property of this equation. If you add, for example, sedimentation so that the raindrops can fall out, then this assumption is actually not valid anymore, or the similarity is not exact anymore. And then the parameterization might actually develop or have biases that are quite significant. So yeah, I think in this box model framework, it's pretty much impossible to beat this parameterization in its behavior, because it makes this clever use of this similarity, and you would need a machine learning model that can also make use of that to probably to be in a similar accuracy. But if you would go to more complex problems, and even a 1D model might be already sufficient for that, then you will see biases in the bulk scheme, and maybe you can improve then over that. But to be honest, I see the use of the machine learning more in the more complex problems, for example, with the ice microphysics, which is not saying that you shouldn't look at this warm rain problem, because it can be used to test more advanced techniques and algorithms and develop them and understand them. And if your machine learning algorithm can improve over the simple approach that I used for this problem, then of course it would be also really nice then to use that kind of algorithm for ice microphysics problems. Yeah, where our current bulk schemes really still have big biases and problems.
Interesting. Okay. Thanks a lot. That was quite an illuminating answer. Another question from the chat. How do you calculate the score? I'm guessing this is the objective function. And did you train the neural network with all inputs or just pick some variables?
So these are actually two questions.
That's true.
So we the training of the neural network. I'm still sharing my screen, I think.
Oh, yes.
So what we did here is that we tested different predictors, going from very simple, using just two model variables as predictors, like liquid water content and mean size, then adding the shape parameter, adding the rainwater content, and so on, getting to the complexity also that bulk parameterization. Yeah, there are actually not more variables or predictors that we can add, because that's all the predictors a two-moment scheme has available. So that's all we could do at this stage. And for the actual training and for the process rates, this was actually doing fine, as this figure shows. And then the other question, I think, there's the question, which score actually? So these scores are just the scores against the process rates, which is also kind of what we trained with. But here, of course, we use independent testing data, but it's the process rates. And here the neural network is doing really good. That's also what it was trained for. But then here, we do the ODE solutions, and then we compare to the Superdroplet benchmark solutions. And but here it didn't actually show scores, but there are scores then in the paper. But then we compare with the Superdroplet benchmark solutions of the whole time evolution. So yeah, that's how I would answer the question.
I see. Okay, thanks. Any other questions before we close?
Yeah, maybe one quick question or more of a remark. I understand that the ODEs, you solve them with just forward Euler, is that correct?
That's correct. It's very, very simple, yeah.
Just pointing out that forward Euler directly is differentiable itself. So you could, with very few lines of code, have the mean squared error not on the AU, AC, and the other, these 4 variables, but directly between the solution, like that you just show on the left panel. Maybe that helps. So you could have the mean squared error if you look at the red line and the black line and the blue line in the left central panel, which are the ODE solutions, if I understand correctly. You could have the mean squared error directly on those, like at any point in time, which I think would be the more natural, if you do really care about the ODE solutions in the end, which would be the more natural space in which to compute the error, right?
Yeah, but in a neural net, I don't have that. So when I train the neural net.
Yeah, but the neural net gives you the parameters to compute the right-hand side of the differential equation, right? And that then goes into the Euler solver. And the neural network is differentiable, and the Euler solver is differentiable. So you can take a mean squared error on the output of the forward Euler solver and take gradients with respect to the neural network way through all of that. It's pretty much the same trick that neural ODEs use, but you don't have to use the neural ODE framework for this. Just pointing it out because you mentioned neural ODEs in the discussion.
Yeah, but these are really the kind of ideas or techniques that I would like to see being applied to these problems and see whether they will actually do better and give us better machine learning models. But that's kind of where my expertise also ends. That as a, yeah, let's call it domain scientist, I don't have the mathematical background and to some extent also not the time to dive into these details of the machine learning approaches. That's really where I would like kind of in a hand over to the machine learning experts to explain me which methods and approaches are suitable and better and still it may be easy to use. So the neural ODE, I tried a little bit with the Julia package that is available, but it's really difficult to use. And I think it's not yet ready for this problem. So yeah, I'm really looking forward to what the machine learning community will do with this. And this was also my motivation, that I provided the training data and my simple Python scripts and tried to make this as approachable as possible for others to pick up. So
that is a very good point. That data is online as supplementary material, I believe. And so I think probably a number of people in this meeting might find it interesting to see if they could use some different training approach to do better long-term predictions. It's an interesting challenge.
Yeah, that's what I'm hoping for and why I actually published the paper.
Yeah.
Yeah.
So the challenge is out, guys. hopefully in 1 year's time or so, we're presenting another paper on the same topic with some better long-term solutions. Let's see.
Yeah, and as I said, I have already looked a little bit into that, and I decided for myself that these more advanced approaches are too difficult for me. I also have a daytime job at DWD that I have to do, and maybe I will pick up some of the things about ice microphysics, where I can bring in my expertise as kind of a domain scientist again. But I will probably not continue with this swarm rain problem myself.
Well, hopefully some other studies will come up with better tools for fitting these parameterizations based on their long-term behavior. And once those tools are working, maybe you can come to it again with more complex physics, different kinds of particles, and we'll see.
Yes, exactly. That's what I would be hoping for. Of course, there are some people that would then say, oh, then you are introducing just compensating errors and so on. But I think that's a too negative point of view. So if we restrict ourselves to simple models, we have to get the best out of these simple models. And of course, then you can call it compensating errors, or you can call it good long-time behavior. I don't care. I just want a good model. So yeah. Thanks for your attention and for the discussion. That was great.
Yeah, thank you so much for participating. Thanks to everyone who joined. Great. So we will meet again in 2 weeks with another topic to be announced shortly. Thanks, everyone.